Okay, cool. So the basic sort of setting that we are looking at is one where there are users. Users have data, small data, big data, whatever, right? And they want to sort of store it. They want to outsource storage of this data. They want to store it in a cloud, right? So this data could be, all kinds of things. Financial data, medical data. My genome. I might sequence it and put it on the cloud. Who knows, right? The Internet of Things, right? My whole house is generating huge quantities of data, or it will in a few years when I'm rich enough to get a smart home, right? Where does all this data go? It has to be stored somewhere, and it's typically stored away from my computer, remotely. Let's call it the cloud for today, right? Not only is the data stored in the cloud, it's actually computed on. You want to do useful things to this data. You want to do statistics. You want to learn from this data, essentially. Right? So that's the setting of cloud computing. It's a sort of cartoon setting of cloud computing. As cryptographers, security people, people concerned about security, we are concerned about people that might get access to this data one way or the other. There might be hackers, who are not authorized to access the system, but who get in anyway. Or there might be sort of insiders, sort of employees of these sort of cloud services who actually legitimately have access to this data, and they might sort of exfiltrate this data, for example, right? So there are a host of sort of security concerns that come up when before I stored my data in my computer, and now it's away from my computer, right? So that makes me paranoid. All right, so I want security of this data, or some subset of this data, the one that I really care about, that I store it in the cloud, right? So the natural sort of answer, a cryptographer's answer to this question is just encrypt the data. Okay, plain and simple. We have been doing it for like 40 years. We know how to do it fairly well. Let's do it. Okay, that's great. But remember, we said we also want to compute on this data. So you have two concerns here. We want to do computations on this data, derive sort of useful results from it. So that's on the one hand. And security is on the other hand. And they don't seem to go well together, right? How do you compute on the encrypted data? If I know the data in the clear, I can run my program on it. But what in the world, right? I mean, it's encrypted. It's in a box, right? What do we do? So, the common wisdom, probably not to cryptographers, but to the outside world, to the world at large, is that these two concerns are diametrically opposite to each other, right? So when you want usefulness, you have to sacrifice security. You have to open up the data somehow, right? So the point of today's talks as a whole is really to show that this sort of dichotomy is a false dichotomy. Okay, so there are ways of getting both usefulness and security in one go. Namely, there are ways of computing on encrypted data. Right. So the goal of my talk is to introduce you to some of these tools, namely homomorphic encryption, functional encryption. These are special types of encryption schemes that let you compute on encrypted data. We'll get to the details in a second. Okay. And there are other things. We've been actually doing this for over 25 years. There are tools called secure multi-party computation. Again, something you'll hear in detail later today. These are all sort of ways of maintaining privacy of data while computing on it. Okay. For this talk, I'll focus on homomorphic encryption for the most part. I'll also tell you a little bit about functional encryption, and you'll hear about other things, other great things, the rest of the day. Okay, cool. So what is homomorphic encryption? A lot of you probably know what this is. So I'm going to go a little bit fast, but if you have questions, you should feel free to raise your hand high up so I can see you in the crowd of people, please feel free. Okay, cool. So what is homomorphic encryption? It's an encryption scheme. There is a key, there is data. I encrypt the data with a key. Okay, that's a regular encryption scheme. Store it in the cloud. And now the point is there is a way to take this encrypted data and the computation you want to perform. So that is, running support vector machines, let's say, on this data. Right? It's a fairly simple computation. You want to take the encrypted data, you want to take a computation, you want to do the computation on the encrypted data, and what do you get out of it? You don't get the result, you get the encrypted result. You as in the cloud. The person who is doing the computation gets the encrypted result. Right? And they send it back to this person, the user, who knows the key, so she can open it up, she sees the result. Done. Right? So really the magic portion here is what's happening on the cloud, namely a way to take encrypted input, a function, a computation, and produce the encrypted result of this computation. Okay, so that's what's going on. This looks like magic. If I erased my memory, I started sort of doing computer science from scratch, it would blow my mind, to tell you the truth, right? It would really blow my mind. But you start doing things, and then you realize that you can do it. In fact, practically every encryption scheme, public encryption scheme we know, is homomorphic in one way or the other. Right? So this is the Goldwasser-Micali scheme, which really sort of started the formal study of cryptography. It's additively homomorphic. You can add ciphertext, you can add plain text mod 2 inside the ciphertext. Right? So that's a simple computation, but that's nice. It's a useful computation. Then a whole bunch of things. You can multiply, you can add small numbers, you can add large numbers, you can add and then do a little bit of multiplication, namely one multiplication, and so on and so forth. So people sort of made progress, step at a time. Very nice, right? In supporting more and more complex computations on encrypted data. Really, the question is, can you do interesting, sophisticated computations on encrypted data? In particular, can you do all computations you want to do on plain text data? I now want to do it on encrypted data, right? So that's called a fully homomorphic encryption. Fully means, thank you very much. You give me your favorite computation. I'll do it on encrypted data. Okay, so can you do it? That was the question. And thank you to Craig. A few years ago, Craig Gentry discovered a way to do this, to construct a fully homomorphic encryption scheme. Okay, so what happened then was a flurry of activity. It's Zvika Brakersky, my good friend. And the way I think about it is that we went from a very nice homomorphic encryption scheme. We didn't know how to do it before. Post Craig, we know how to do it, right? But the scheme wasn't particularly efficient. It wasn't based on sort of security assumptions that we were comfortable with, right? All these things changed in the span of a few years. So I think about the process is going from vacuum tubes to transistors, maybe, right? I mean, somewhat preposterously, but it's a fairly accurate analogy. So in particular, we now have new frameworks to construct homomorphic encryption schemes, even fully homomorphic encryption schemes, which offer both better security and better efficiency. So typically in life, you give up one for the other. Not here. Okay. These schemes are based on sort of shortest vector problems, on lattices, on ideal lattices sometimes. And they, for the best of our knowledge, they offer security against quantum computers. Future in a sort of a dystopian future when quantum machines come into effect and they break all our other crypto systems, it still remains secure. Right? So, and they're as efficient as you can get asymptotically. Okay, so if you sort of measure complexity, asymptotically, the overhead of homomorphic computation, namely the time it takes for homomorphically computing a function divided by the time it takes to compute the function, on plain text, is polylog in security parameter. So, this is as good as you can get. Now, there is a big gap between that and actually, practical sort of homomorphic encryption schemes. But in theory, we can get as good as you can hope for. Right? Good. So that's the state of affairs. What I want to tell you is a little bit about how this is done. Okay. Okay. Good. I'm going to go a little bit fast on this because you likely know what's going on here. Here is a very simple encryption scheme where you can add encrypted numbers. Right? So you have a group of some group of a prime order P, and your public key is a number G in this group. It's called a generator, and G to the power X. X is a random number, and X is the private key. Right? So this is the Al-Gamal encryption that you all know and love. Most of you know and love. How do I encrypt? I pick a random number R. I compute G to the power R. I take the public key G to the X, raise it to the power R, so I get G to the power XR or RX, same thing, times H to the power M. H is another number in the group. Right, that's how you encrypt messages. In fact, this is really sort of Diffie-Hellman in undercovers, if you think about it. All right, so this is additively homomorphic. This is sort of born additively homomorphic, right? I don't need to do anything to it. Namely, if I take two ciphertexts that look like this, R1, that encrypts M1, this that encrypts M2, and now what do I want? I want to construct a ciphertext that encrypts M1 plus M2, the sum of the two messages, and what I do is I simply multiply these component-wise, right? So I multiply these two, stuff adds up in the exponent, and I get what I want, right? That is an encryption of M1 plus M2. Now, the cryptographers among you, I see Hugo is peering at it. This is the one problem with this encryption is that to decrypt it, eventually I take this number, raise it to the power X, divide it out of here. X is the secret key. When I'm decrypting, I know the secret key, right? I get H to the M, and then I have to somehow find M. And what is the process of finding M? It's computing discrete logarithms. But wait a second, discrete logarithms are hard, aren't they? Turns out that, there are two ways of solving it. You can either work with small messages. M here is small. I mean, they're 0, 1s, they're small numbers. Then you can compute discrete logarithms easily. Or you can tweak the scheme a little bit. I'm not going to tell you exactly how, but what comes out is called the pair encryption scheme, where you don't have to play this game. You can actually compute discrete logarithms to the base h, while maintaining the property that discrete logarithms to the base g are hard to compute, right? So that gives you security. On the other hand, h gives you correctness, gives you decryption, right? So this will let you encrypt numbers, bottom line, and you can add encrypted numbers to your heart's content. I mean, as many as you want, right? Good. Right? So if you have an application where you're only concerned about computing sort of means or things of that nature, you should probably be using this. Okay, so that's additive homomorphism. Let's make a huge jump all the way to FHE. So I'm not going to tell you the gory details. In fact, actually, it's not that gory. As time passed, these schemes became simpler and simpler and simpler. And what I'll tell you is FHE in a minute. So again, it's not going to be full details, but I at least want to give you an idea of how these things work. Okay, so baby-proof, hopefully. Babies these days know eigenvalues. That's my. I don't have a kid. We'll see. All right, FHE in a minute. So how does this work? This is based on an encryption scheme of Gentry, Sahai, and Waters. A beautiful, beautiful scheme. And this is something that they call an approximate eigenvector scheme. Okay, so what does that mean? Your ciphertext in this scheme is an n by n matrix, a square matrix with 0, 1 entries, but for the moment you can forget about it. The secret key is a vector of length n, right? So you can multiply these things together. That kind of makes sense. And what does a ciphertext look like? I'm not going to quite tell you how to generate how to encrypt a message, how to generate the ciphertext of a message, but I'm going to tell you what it looks like. Right? That's all that's important for today. Right? A ciphertext of a message M has the property that when you multiply it with the secret key, this makes sense. It's a matrix, it's a vector, you can multiply them together. What you get is a multiple of the secret key itself, where M is really a number. right? I'm encrypting numbers here. So ciphertext times the secret key is a vector, and that should be a multiple of the secret key itself, approximately, right? So, a little bit close to a multiple of the secret key, right? So that's called an approximate eigenvector scheme. Why is it an eigenvector scheme? Because if you look at this equation without this wiggly sign, this says that the secret key is an eigenvector of this matrix, the ciphertext matrix, with eigenvalue equal to the message. That's exactly what it is. Right? Beautiful scheme. Now, without this wiggly sign, the scheme is actually insecure. If I give you the ciphertext, you will know, you'll do linear algebra and you'll figure out what the message is. But with the wiggly sign, things become secure. Okay, things become actually quantumly secure, and things become secure even against exponential time adversary. Okay, so you gotta trust me on this. Okay, so again, we are friends, so let me remove the wiggly sign and let me show you how to do homomorphisms. Okay, and with the sign, with the error, with the approximate sign, you need to do a little bit more work, but not all that much. You can do it. How do you do additions? You have two ciphertexts that encrypt message 1 and message 2. You just add the matrices. That's it. When you add the matrices, the eigenvalues have the property that if two matrices have the same eigenvector, their sum also has that eigenvector, where the eigenvalue is the sum of the eigenvalues. Okay, beautiful. The same thing with multiplication. You can also multiply matrices with the same eigenvector, and you get a matrix with the same eigenvector, and the eigenvalue is a product of the eigenvalues. Here is a proof. It's an exercise to do this. Okay, so that's it. That's that. I'm done. I mean, I showed you how to construct an encryption scheme, modulo details, where you can add and multiply encrypted numbers. Now, if you can add and multiply encrypted numbers, you can write everything as a combination of additions and multiplications, case closed. Okay? So really, any computation, so additions and multiplications are Turing complete. You can write anything as a combination of these guys. Oh, wow. What is that? All right. Good. So that's it. That's homomorphic encryption. 2 slides. It took a long time to get here, but we got here. Right? The catch is that this scheme is not something that you should go back and implement and use. Right? It's a nice scheme to understand. It's a very simple scheme to understand. But the point is that it only encrypts. What does it encrypt? It encrypts a number. It encrypts a number, and it becomes, when it's encrypted, it becomes a matrix. Now, that's a lot. Right? It's a huge message expansion. We don't really know good ways of getting around it. Right? So it has large ciphertext expansion. Unfortunately, that's still the case. It's a very nice open question to make this simple scheme also efficient in this sense. But there are other schemes which have smaller ciphertext expansion. Something that this is an encryption scheme with Craig and Zvika, and this is what's implemented and used in practice. Right? So that's it. That's homomorphic encryption. Okay. So let me tell you a couple of tricks that you can that we use to speed things up in practice. One is that let me look at a setting where the user is really your Fitbit. Okay, so it's a small device. The guy can barely stay alive, with the battery power and so forth. It can encrypt it can maybe do AES encryption, stretching it. That's about it. Right? I cannot ask it to do FHE encryptions. So what do I want to do? I want this guy to take measurements, continuously take measurements. My heart rate, what distance I walked, my GPS coordinates, so on and so forth. Encrypt it, send it to the cloud, and the cloud can do analytics on this encrypted data. That's what I want to do. But the guy cannot encrypt with FHE. What do I do? Turns out that you can do the following trick. You can encrypt the data with AES, right? With the regular sort of private key, encryption scheme. We now even have sort of, Intel instruction sets that can do AES operations natively, right? So these things are presumably much more efficient than homomorphic encryption. So let him encrypt with AES. And on the side, I'm also going to ask the guy to encrypt the key of the AES, the same key, with the homomorphic encryption. So this is a one-time process, right? I mean, so the device doesn't have to do it. A computer or my iPhone can do this, the second part of the computation. The first part is something that the device does on a continuous basis. Right, so now I want to compute. So how do I compute? Well, I mean, the data is encrypted under AES. I have no clue how to compute with AES. AES is not homomorphic. If it were, I'd be, jumping up and down with joy. It's not the case. So what do? I want to convert somehow this AES encryption into a homomorphic encryption of the same data, right? And then I can compute. Right? That's the idea. And how do I do it? It's a cartoon picture, right? You have two encryptions, one of the data under a key and of this key under key 2, right? So this is the AES encryption. The red one is AES encryption, and the blue-green one is the homomorphic encryption. So how do I do this conversion process? It's very, very simple. You can wrap things. You can think about these as onion layers, right? So you can wrap the ciphertext under a homomorphic encryption, right? The blue-green box. And now you have two ciphertexts, one encrypting key 1 and the other one encrypting the data, the AES encrypted data under key 1. Right? So now I can compute. Now I can do computation. In particular, I can do AES decryption under the homomorphic encryption, and that's it. That's the end of story. I get the encryption of the data, and once I have the encryption of the data under homomorphic encryption, I can compute. I can get the encrypted result, send it back. Right? So the point is, the bandwidth, the computation time for the encryption is essentially negligible. It's as much as you would do it anyway, right? Encrypted AES. The bandwidth is also pretty good because all you transmit is really the AES encryption of the data, right? These are things that we know how to optimize. You pay a price, which is this price of converting, encryptions from AES to homomorphic encryption, but this is done in the server. It could be done offline, right? So this is something you can do. Yes, start.
Can you count the result as part of the
I do. But the result, I'm going to think about the result as going to your iPhone, right? Which can process it. You can see a pretty screen where it shows you this graph of how much you walked over time. But the data is not generated, on the iPhone. I mean, I want.
So the Fitbit uses AES, then gets a result and passes it to some iPhone. Will it decrypt it or something?
No. So the Fitbit encrypts with AES, and when the result goes back to the iPhone. And so think about the Fitbit and the iPhone sharing a key, an AES key, and. Right, so, you can do tricks, essentially, right? Good, so this is one. Optimization 2 is something that's far more interesting. And this is one where you can get around this limitation of the toy scheme that I talked about. Namely, you can encrypt many messages in a single ciphertext. So you should think about the ciphertext as composed of slots, right? So essentially, there's as many slots as elements of the ciphertext, numbers in the ciphertext, and each slot can contain a message. Right? So you're really sort of packing the messages to capacity in this game. And SIMD means that you can compute in parallel, right? In one computation, in one operation, you can add a bunch of numbers in parallel, a vector of numbers to a vector of numbers, and you can also multiply a vector of numbers to a vector of numbers. And now you can do computations this way in parallel on a large amount of data, right? So the point is, the latency of this computation is going to be governed by how much time it takes to do a single computation, but the throughput is, how much I can parallelize, which is quite a lot. And you can also do other sort of very interesting things. You can encrypt a vector of messages, and you can compute functions of these messages within themselves without kind of unpacking them into different ciphertexts. that's something that's very useful again. Right, so you can put these optimizations together, and there are many, many more. And most of these are sort of started from a work of Gentry, Halevi, and Smart back in 2012. Right, so you can put them together and implement FHE, right? Is Shai here? No. Okay, good. That's all right. So we now have an implementation of homomorphic encryption called HElib. It's an open source library. And again, this is based on the BGV scheme, which I did not describe. It's not the toy scheme. But it's a more efficient sort of scheme where you can pack many messages plus optimizations. Right, and there are many, many others. So once you start, the floodgates open. We can implement sort of other kinds of homomorphic encryption. And by the way, there are many, many homomorphic encryption schemes. They all sort of work in with similar mathematics. Some are more efficient than the others, and there are implementations of essentially all the most efficient ones. Right, so there are a whole bunch of these sort of software, open source software that if you are the kind of person who is interested in sort of playing around with it, you can at this point. Right, you might be traumatized at the end of it since Shai is not here, and it's not being recorded. But the fact is that there are these things, and they are continuously being improved. Okay, so this is implementations. I am not going to show you. Well, so essentially, I mean, so forget about the columns in this table. Just look at the encryption, decryption, and essentially homomorphic additions and multiplications, which is really re-encryption here. Encryption takes off the order of milliseconds, so does decryption. And homomorphic additions also take off the order of milliseconds, actually lower order milliseconds. But multiplication will take you about hundreds of milliseconds. So that's really that's common across all the sort of implementations. Right. Good. Yeah. So we have a few applications, but really, we're only starting to do this. We are yet to see a robust suite of applications, like real applications, using homomorphic encryption.
These applications are academic papers, or?
Yeah, they're academic papers. This VoIP thing was done as part of the DARPA program, so it's not an academic paper. It's tough. I wouldn't call it open source, though. I'm told that it's being used somewhere. I have no idea where. But the machine learning is an academic paper, right? It's Raluca's paper. Good. So it's basically adding signals, right? So you speak into your phone, generate signals, digitize it, encrypt it, right? So and it goes to.
What do they need FHE?
Just additive homomorphism. Just additive is good enough. Yeah, absolutely.
Can they use by air?
Yeah, probably, but they used lattice encryption in any case.
I think they
But essentially, I think it was addition. That's my understanding. Maybe they wanted to sort of do more with these signals, but eventually they ended up just doing multiplexing of these signals. Okay, so that's what it is. So the bottom line of all this is that there are tools out there, thanks to largely to Shai and Victor. You should feel free to play around with it. Good. Great. So how much time do I have, Tal?
30 minutes.
Whoa. Okay. All right. That's, okay. Good. So let's take it easy. Good. So that's homomorphic encryption, right? So one could ask, is homomorphic encryption the end of the road? Have we achieved salvation? Shall we go home and meditate? That's not quite the case, for many reasons. So let's think about homomorphic encryption, right? So Alice encrypts data, sends it to the cloud. The cloud can do computations, under the encryption. Really, it sort of evaluates circuits, Boolean or arithmetic circuits under the encryption, and it gets the encrypted result. Right? But really, this is an all or nothing process in the sense that the only person who can access the results of this computation is the user. Right? If you have the key, you can open, otherwise you can't. This is a very all or nothing object. And that causes problems, right? I mean, that is something that doesn't always work. For example, this is my other cartoon application. So let's say you have a pacemaker, right? The guy sort of measures my heart rate, right? My signal, encrypts it in a future, sends it to a cloud. And the cloud wants to do the following, right? It wants to see if my heartbeats, my average heartbeats over a day, maybe weighted average, if it's more than a certain number, it's saying, well, look, this guy is in trouble. Maybe I should contact someone responsible, right? So how does the cloud figure this out? Well, I don't know. I mean, it can encrypt. It can compute on this encrypted data, but what does it see? It sees an encrypted result. It cannot do anything with this encrypted result unless it is sent back to the user. And by the time the user, I don't know, right? So not so cool, right? So what I want, so you can really think about this is just a cartoon. You can think about computing functions, on the sequence of signals. So what I want is something called functional encryption, okay, where the idea is that the user, again, the smartphone, not so much the pacemaker, can generate a functional key, a key that is, it's not the original secret key, which can decrypt everything, but it's a special purpose key that is tied to a certain function. It can compute this in the beginning of time, right, when things are set up, send it to the cloud. And what the cloud can do is it can take this encrypted sequence of data, sequence of signals, and the secret key for this function, functional secret key, and compute the function. This is not X, sorry, this is the data. Right? So it can compute the function, the one function on this data. Right? So this is a functional key because it lets you compute the particular function on the encrypted data, but nothing else. Right? So it reveals f of x given encryption of x and only f of x. Right? So that's what you want. In this example, the cloud can figure out just this one bit of information on what's going on. Okay, good. So that's functional encryption. Beautiful idea. Again, it was introduced back in 2005, and there's a steady sequence of results, which I'll tell you in a little bit. Okay, so before I go there, parenthetical remark on something that this whole description sort of hides, and something that you might be wondering about, right? So I said the cloud can learn a function of the data, a function of these signals, when it's given the secret key, functional secret key. But what is this function? Right? Who chooses this function? Right? So it's a very fact that it can learn this function of the data means that the data is leaking. Yes? And if the function is not chosen carefully, perhaps it leaks too much. Right? The output of this function might itself be intolerable amount of leakage. Right? So really what this suggests is there are two questions that one should be asking here. One is, I want a certain outcome, okay? I want to do a certain process, I want to learn something. One, how do I choose the right function, the right concrete function to compute on the data, right? And two, given a good function, once you manage to design something like this, which Adam will tomorrow, how do I compute it securely on encrypted data? Right? So these are orthogonal questions, and answers to one will, can be combined with answers to the other to get what you want. Right? So I would call this somewhat arbitrary names, but just following the terminology in literature, I would call this data privacy. How do I choose computations which leak as little as possible? while still giving me an answer, a meaningful answer. And data security, which is, given this function, how do I compute it on encrypted data while revealing only the output of this function, nothing else. Right? So that is functional encryption. You will hear a lot tomorrow about the first of these questions. Okay, so that's a parenthetical remark, in case you're wondering. So what is, this is functional encryption. I just told you about it. What is the state of the art? So it turns out that the state of the art is much less mature in functional encryption as it is in homomorphic encryption. Right? So there are very efficient sort of special cases of functions that you can compute. You can think of identity-based encryption as an example of functional encryption. So you kind of delegate different types of access to different people. You're not really computing functions, but you're letting different people access different data, really. Searchable encryption, which you will hear about with Hugo and Raluca and David today. Attribute-based encryption is yet another sort of specialization of functional encryption. All these things have sort of implementations. They can be made fairly efficient. On the other hand, sort of general purpose functional encryption, right, like fully homomorphic encryption, I want fully functional encryption, and that has, we do know sort of solutions in theory, but they are far off in the sort of theory land at this point. And there's a lot more work to be done to make these things efficient, even bring them to the point of homomorphic encryption, where one has hope of writing code. That's not where these things are at. Okay, so efficient general purpose functional encryption is a major open question in cryptography. Let me say one more thing about functional encryption. So the general idea of functional encryption is to leak special functions, various functions of data. Why? Well, in our example, that was basically to enable the cloud to take actions on behalf of the user. Right? You could use functional encryption like objects for other purposes. For example, perhaps leaking a little bit of information about the encrypted data might actually make computation on encrypted data faster. Right? I'm not hiding everything from you. I'm telling you a little bit one at a time, and maybe you will do the encrypted computation faster as a result. That's a different motivation to do functional encryption like objects. Order-preserving encryption is one such. But I want to say that one has to be very careful about what information you leak, right? And in particular, when you put together a few sources of information leakage, who knows what can happen, right? So there's a promise of efficiency on the one hand, but there is a devil of information leakage on the other. One has to be careful, not saying you should abandon this, but one has to be very careful in how to apply this. Right? You'll hear about it again in various talks. Good, okay, so I started off thinking, who do I give the talk to? Cryptographers, general audience, I have to balance something out. So I have to tell you something new, right? Newish. And here is my 2 slides of new sort of crypto. So let me show you how to do functional encryption for linear functions, right? So if you think back to our example, the example was to compute the weighted average of a sequence of signals. And that's a linear function, right? In fact, I'm cheating a little bit because all I wanted this guy to compute was to say if the weighted average is more than a certain number or less than a certain number. That's one bit of information. I'm actually going to let the guy compute the weighted average. Why not? Okay, that's all I know how to do. So why not? Okay, so good. So this is a very interesting sort of work of Abdallah and others, recent work. So how do you do this? How do you do linear functions? How do you do functional encryption for linear functions? Okay, so all I'm going to use is El-Gamal encryption. Okay, so I'm not going to throw new math at you. This is what you've seen already. How do you do this? So the master key of the device is an AES key, right? Is an AES secret key, and some randomness R. The device encrypts, right? I mean, the device encrypts for every sort of time period. For every time period, it generates a new AES key, sk sub t, as a function of the secret key, as a pseudorandom function of the secret key. How do I encrypt? I do Elgamal, essentially, right? So I do G to the R, the same R. I'm going to reuse the same R over and over again. And I do G to the R times this time-specific secret key times H to the message, the signal that at time t. Okay. What are the functions I want to sort of do functional encryption for? These are weighted sort of summation functions, right? So weighted addition functions. And what is a functional key that lets me compute this weighted summation function? It's the weighted summation of the secret keys, of the time-specific secret keys. Right? So imagine that today, the device transmitted 1,000 sort of messages and generated 1,000 secret keys, sk sub t. This is a weighted summation of 1,000 of these secret keys. Okay, so how do I, how do I decrypt? I'm going to take a whole bunch of these ciphertexts, right? There's one for each time. I'm going to multiply them together. I'm going to homomorphically multiply them together. And now, the way I set things up, this scheme is key homomorphic, right? So these guys are all sort of encryptions with the same randomness, but different secret keys, and they're encryptions of different messages. But yet, I can multiply them together. I can sort of add in the exponent the secret keys, and I can add in the exponent the messages. I can operate on ciphertexts encrypted under different keys. Okay, that's the cool thing about Elgamal. The point is, so eventually I'm going to get G to the R times the summation of the secret key times H to the summation of the messages. Now I have the summation of the secret keys. I can decrypt, and what do I get? I get the summation of the messages, the weighted average of the messages. That's it. It's a beautiful, beautiful scheme. Now, there are several optimizations that you can do to this scheme. You might ask, how complicated is it to compute this functional key? I really have to sum up the 1,000 AES, the 1,000 secret key sub t's, right? So who does this? I mean, if the device does it, it's in trouble. If the iPhone does it, maybe it's okay, but still I would like to optimize it. It turns out that you can make this computation, the size of this computation proportional to logarithm in T. Logarithmic in 1,000. Right? So I'm not going to exactly tell you how much. You know what? It's an exercise. I thought about it in the shower today, so it must be an exercise. Good. Yeah, good. So you can do FE for linear functions, and pretty much that's it, actually. It's a sorry state of affairs. This is pretty efficient, I would think. I mean, I haven't implemented it, but you probably can. But that's it. That's where efficient functional encryption ends. So this is a major, major research question to make functional encryption more and more and more efficient, at least bring it to the level of homomorphic encryption. Okay, cool. All right. Good. So I've told you two things. I've told you homomorphic encryption a little bit, functional encryption also a little bit. Now let me tell you one more thing, and that will sort of end my talk, and that'll hopefully sort of pave the way for other people who have real things to say. Okay. Let me tell you about multi-party computation. So far, when we talked about computing on encrypted data, it was a very non-interactive process, right? I encrypt it, send things to you, and you can compute and send things back to me. Very nice, right? One message each way. That's it. Turns out that if you allow interaction among two parties, among many parties, things can become much more efficient, right? The math that you use becomes simpler. Things can get a lot more efficient, and that's something I want to tell you about. Okay, so what is multi-party computation? Let me change the motivation a little bit. The problem here is that there are multiple people, each with their own data set, and they want to compute together a function on these data sets. but they can't send these data sets to each other for whatever reason, for privacy, for legal reasons. You will put me in jail if I send you my data because it's not my data, it's my customer's data. Economic reasons because, well, data is power, right? The fact that I have data means that I'm better than you, or the other way around, you're better than me, right? So why would I send you my data? Good, right? So this is what I want. Compute, each person has an X. They want to compute together, keeping the privacy of these X's. Right? So I would put this under the umbrella of computing on encrypted data. I'm going to repurpose. I'm going to co-opt a secure multi-party computation as a way of computing on encrypted data. Right, so here's an example. Hospitals, pharma companies, Broad, MIT, the NIH, they each have data sets belonging to people, users, let's say genome sequences, and they want to compute a genetic marker for a disease. So this is very, very important, right? This is really sort of pressing concerns today. The fact that more and more sort of genomes are sequenced means that we can make these predictions better and better. We can find better and better markers, which is very, very important for society at large, right? So this is very, very important that people are able to pool together their data and compute collectively. Good. So this is an example of something that we want to do, right? So genome sequences, I want to compute together. Good. So for the non-cryptographers in the audience, I want to tell you very quickly how this is done. Sort of, again, a cartoon example of how this is done. Actually, it may not be cartoon. It might actually, this kind of computation might actually be what you want to do in practice. So this is, the example is computing the average of a bunch of numbers. That may not be, that might actually be what you want to do for the most part, right? It's a beautiful idea of due to Michael Rabin. So let's say you have three parties. They each have numbers, x1, x2, and x3. Let's let them denote salaries, right? 8, 10, and 12, with a few zeros. And how does this work? Each player, each party is going to choose at random three numbers that sum up to its salary, right? Modulo a prime number and whatever, but let's forget about it for a moment. Okay, it's just three numbers. 5 plus 2 plus 1 is 8. That's all I want to know. Right, and so on and so forth. Each person does this independently. And the players send, each player has three numbers. A green number, this is green. Hugo, you're not going to know, but this is purple, this is red. Okay, so there are three numbers. And I send the green number to one party, the purple number to the other, and the red number to the third person. Okay, so that's what I do. That's what each person does. And now, how do you compute? Each person gets three shares, three numbers from three parties, one from himself, right? And they sum up these numbers. That's it. Right? So addition has this beautiful property that no matter whether you add column-wise and then row-wise, or row-wise and then column-wise, the result is the same. Mind-blowing, right? And that's exactly what happens here. If I did my math correctly, they each get a number, they send it to all others, and the sum of these numbers is really the salary, the sum of the salaries. Okay, so this is the earliest multi-party computation protocol back from the 80s, but this is still beautiful, very relevant today. Right, so it turns out that that's not all you can do. You can do everything. You can compute any n-party function, n-people, n-party functions, even if you can do this securely in the sense that each person gets the result and his own input, but nothing else. And you can do this even if many people collude, try to pool together what they see and learn stuff. Right? You can do that. Even if a minority of people collude, any minority of people collude, you can do this without any cryptographic assumptions. So this is really, the math used here is very, very simple. It's very close to the addition, the average salary example that I said. And this could potentially be the thing to do in practice. I mean, who cares about collusions? I mean, I'm not, who cares about collusions? Okay, so yeah, okay, great. more, Mike and others will tell you, Sanjam and others will tell you more about it in the afternoon. Okay, and there are applications. There are no tools that you can download and do MPC as far as I know. You should correct me if I'm wrong. But this has been used in various settings, in a couple of settings at least. One is to, the city of Boston, they decided they want to figure out the income gap between sort of men and women, between various ethnicities. They want to do things to improve the state of affairs, right? Now, it's not good enough to improve the state of affairs. You have to measure how well you're doing, right, to gauge your progress. And what does gauging your progress mean? You compute sort of averages, you compute statistics on sort of the collection of salaries of these companies. So the data belongs to a bunch of companies, right? And you want to compute a mean or average, mean or standard deviation of these numbers. This, it turns out, it's an application. It's actually something that has been done. There is something to there's something to say about writing an algorithm. There is something else to say about actually writing a tool that people can use. And that this is an example of something that's been done. Danish auctions. It's great. Right. Cool. All right. So that's all really I had to say. We've seen a lot in cryptography. We will see a lot more. We now have very powerful cryptographic tools, homomorphic encryption, functional encryption, multi-party computation, many more that you will hear about today. That can get you both functionality and security on the same token. That said, it's a very it's like that knife. It's a very complex set of tools, and determining what to use when is a very big question. I mean, this is something that I probably will take a couple of days to figure out, if at all, to figure out what's the right tool for a particular application. Right, so there's a lot of work to be done here, both to make things practical and to help people actually use these tools. And that's that, and thank you.